Okay, let's go. So today we're going to continue on the address translation mechanisms. So we're going to cover segmentation we covered last time. So we will just quickly recap what it is, and then essentially we will cover paging, right? So there is a little bit of announcement, right? So we decided that our midterm will be next week, right? And so what we're gonna do is we're gonna hold it on October 27th at exactly the same time during our time class. The midterm will be available. I'll give you 1 hour, 20 minutes to answer a collection of questions on grade school, right? So midterm will be on grade school. So, however, on Monday, on the 25th, we'll do some midterm reviews. Essentially, I will spend a lecture on solving previous midterms, showing you how it works, just so you feel more comfortable about it, right? But we change midterms from year to year. Are there any questions about the midterm?
Yeah, what percentage of our grade is it? Some?
It's like 10.
Like 10?
Yeah.
I like that.
You think like, okay, why do I even have to take it, right?
Well, I just like low stress.
Yeah. Well, yeah. Don't be stressed about it. I mean, first of all, I'm very lenient grader, right? So, I mean, I understand that the class is relatively hard, and it's not about like chasing you, right? So it's about trying to teach you something to the degree possible in this short time frame. Type of questions. So you have to. Oh, sorry. Yeah. So don't be stressed. So usually everyone gets good grades in this class, and I don't remember anyone failing. So what does this percentage? 10. I say 10. Final is 20 though. Get scary for final. Scared for final. Quizzes are 15 and homeworks are 55, right? So type of questions. So we'll cover it online. There will be examples here. You can see. Okay, maybe we haven't put them yet online, but previous years, if you go to spring 2020, like here, you can go, first of all, examples from previous years. And yeah, I guess last year we gave it on Gradescope as well, and I didn't put it back online. So I will ask Claudia to essentially take a look. These are the questions from previous years, right? So you can look through them. They're public, right? So they're different though every year. And I will pull up the examples from Gradescope from last year, so you can have a complete picture. Are the questions submitted directly on Gradescope? Or do we need to answer them in separate documents and upload it to Gradescope? No, everything will be answered on Gradescope. Yeah, that's again that like, I don't know if it's advantage or disadvantage of this remote setting, right? So normally I would give it in class. You would like this printout of this PDF, you would have to write it down by hand. But here since we're going to be using Gradescope, everything, even like open-ended questions, you will have to just type in on Gradescope. Just make sure that you understand the logistics, you start on time, and you will have 1 hour, 20 minutes right before the next class you have to finish, right? Any other questions? But yeah, in case I forget, and I might, can you ask Claudio on Piazza to, actually I learned that you can tag people on Piazza. So you can tag me. So if you actually use the rich text editor and you say like, what is that? @ symbol and then Anton Burtsev, then I will receive a direct email saying that, okay, someone mentioned you. So if you really want my attention, you can also do this, right? So I look through Piazza, but typically only answer the questions which are not answered. What else? That's it probably. So get back to lecture. Everyone is happy. How many questions? I don't really know. So there will be like sized, there will be small questions, bigger questions. So there will be sized proportionally to 1 hour, 20 minutes. Again, just go ahead and take a look at the exams from previous years. I think This class was always formatted to be 1 hour, 20 minutes. So the exam is always targeted towards 1 hour, 20 minutes time frame. You can also look at the sample exams from 143A, but they tend to be a little bit lighter compared to this class. Okay, ready to start? Okay, so logistics all clear. Let's get back to segmentation, right? So remember what we were working on. So we said, okay, look, we want to provide an illusion of a private address space to a program, which means that in the end, we want to run 2 programs on a single piece of hardware, right? So if you have one single memory, we somehow want to say, look, this region of memory belongs to you, and this region of memory belongs to you, right? To 2 different programs, right? So P1 and P2. And we came up with this idea of segmentation, right? Which Intel implements, and many other CPUs implement or used to implement in the past, and sometimes still implement for backward compatibility reasons, right? So the idea was that we will introduce a new addressing mode, which is called logical addressing, right? It will consist of 2 parts. The selector will be in a special register, like a code segment, data segment, stack segment register, and the selector will be used as an index in the descriptor tables, a special table maintained by the operating system, from where we're gonna read the base, and then we're gonna add this base to all the addresses which the program uses, right? So if you have an address in registers or as an immediate value inside the instruction, like a constant, so essentially instead of like going straight and reading X, address X from here, right? The base will be added to your address by the hardware. And so essentially you go and will read this location, which is X plus base, right? And also segmentation unit in CPU in silicon will also check that your X, that you cannot access the memory outside of the bounds of this segment. So each segment has a address 0 and then goes up to the max address, right? Okay, we good on that? Cool. So this is the recap, right? And now imagine I talked about that we use special segment register to essentially index into this global descriptor table. But now let's think a little bit about what is wrong with segmentation, right? So what kind of limitations it have? So the advantage, of course, of segmentation, as I was mentioning before, right, is that it does really provide illusion of a private memory. So you literally can say, look, I'm running process P1, right? This is what I was saying last time. This process P1 may be invoked in operating system with a fork system call, right? And the operating system, which I mean runs somewhere in memory as well. So let's draw it over here, for example. So this is the kernel, right? So really control goes somehow to the kernel, right? Through an interrupt and exception handling mechanism, right? But to implement this fork, what the kernel can do, it can just simply create a new segment with a new base. If this was a base 1, you create a new segment with base 2, right? And both programs, so P1 and P2, will see those addresses starting from 0 and going to the max, right? So they will see them like this. That will be their addressing model, right? So they will see them, and if this is a physical memory, right? So this is their logical addresses will start from 0 and go up to the max, right? The size of the segment. But literally this segment P2, if this is like P2, right, will be just added to all the addresses, right? And to implement fork, you really don't have to do anything. You just simply copy memory from P1 to P2, just with memcpi, just like that, and just then change one value of one register. So specifically register, who can tell me which register we have to change between P1 and P2? Imagine P1 is a parent and P2 is a child. I copied the memory on fork, but what else do I need to do? Who can tell me? You don't remember the interface of fork? Or remember what do we return in the child from fork? Yeah, correct. We return 0 and we have to change the EAX register. Good job. And in a parent, we will return PAD. So essentially in the parent, and why is it EAX? Because this is the calling convention, right? So essentially we know that the functions, according to the calling convention, the functions have to return something in the EAX register, right? That's why the memory stays the same, but the EAX register will be different between these two processes, right? And that's how they're like, but that's how they will be different. And then they will start running different code and gradually, you know, like since their paths will be deviating, the memory will be also changing, right? But since it's backed up by two different regions of physical memory, right, then everything is fine, right? So segmentation achieves this. But let me ask you a question. So what do you think might be like kind of what kind of limitations you see? Like imagine you have this approach and you say, well, segmentation is fine, I can run multiple processes, but what is the inconvenience you believe in terms of building this environment and making it efficient? Who can name a few? I'll put up this figure on the slide so you can just think about it more precisely. We need segments to be continuous in physical memory. We do, right? So that's one limitation. And so what kind of problem you think will arise with the segmentation? Fragmentation. Yeah, fragmentation is one problem exactly because you might have enough physical memory, like maybe this chunk plus this chunk is sufficient to create a segment which is that big, but they are not continuous. This A and B are not continuous, right? So can you solve this problem, by the way, with segments? If you really want to still create yet another third segment which can fit into this in a continuous region, what do you have to do as a designer of the operating system? In segment table, add multiple segments. That's one option, but what if you want to do that? And this is how it was done in the past, to be honest, right? But really, yes, move P1. That's exactly what we can do. Because look, you can always say that, okay, operating system can freeze the execution of this process P1 and say, look, like, okay, I need to move you in physical memory. And essentially this memory can be just copied a little bit, moving it to this region, for example, like creating some free space over here, right? And this is again, since you're copying it in physical memory and you can adjust that base, which is base P1, and just to point at the new location, right? Everything will be transparent to the program, right? The program was temporarily frozen, nothing was running. If it's a single-threaded program, just one thread is frozen by the operating system. And if it's a multi-threaded program, then all threads are frozen, right? But then you can move the segments. But the disadvantage, obviously, is that the segment is kind of big, right? So especially today, we run giant programs which range in the ranges of gigabytes, right? So like up to 4 gigabytes, or if you're using something like genomic workloads, you are happy to consume terabytes of memory, right? As long as you have them on the machine, right? Of course, like you might say, okay, look, but on 32-bit machines, the virtual address space and the size of the segment is limited to the 4 gigabytes, and you're right, but on 64-bit machines, that would not be a limitation, right? But you're absolutely right that you say, like, you can move the segment, but it's cumbersome because it takes time and you have to move the entire chunk of memory. You can't just put this tiny part and say, look, I have control over this tiny part and I can somehow remap it here. And this is how the page tables will be solving this problem, because the page tables will split memory of a process into chunks of equal size. And this size is called a page, which is 4 kilobyte or 4 megabyte on a 32-bit Intel machine, right? We'll get to that in a second, right? But you got the limitation. Let me get to another limitation, very similar. So, for example, this process P1 invokes malloc. And imagine inside malloc says, okay, I need more physical memory. So it invokes SBRK, which goes to the operating system and it says, look, I would be glad to allocate you memory, but really like you're running into another segment over here, right? And at this point, you have to do the same trick. So you can either move P1 or you can move P2, or you can even, if you're really eager, you can even take the entire P2 to disk. You say, look, swapping can be done. You can swap out processes. You say, look, I know that P1, I will freeze P2. I know that P2 is running, but I can freeze it anytime because operating system will have this control, and I will explain how it works. And I will put it to disk. But again, to put the P2 to disk, you have to put the entire segment, right? You can play tricks, right? So you can always say, okay, well, how about I will just go swap out this part. I know that P2 is inactive. I will let this guy run for a while, and then later I will freeze. Like you can do tricks, but it gets a little bit cumbersome, and no one really wants to do those tricks, really, right? Okay, so those limitations, as I was saying, you can swap to disk. So segments are somewhat inconvenient. So relocating or swapping the entire process takes time. And also, as you mentioned, memory gets fragmented, right? So it's just easier to explain it right now for me. So there might be no space or gap for the swapped out process to come in, right? So we already looked at it, right? You were creating and deleting processes. You have a bunch of chunks of memory like we saw in the previous example, but you don't have a continuous segment. And then you have to move stuff around, which is again expensive because segments can be large. Let me stop here for a second. Are there any questions about it? All good? Okay, so this leads us to the idea of paging. So essentially, what is paging? Paging is essentially a mechanism which allows you to, as I was saying, split memory of a process in equal chunks. And each chunk will be of the same size. On Intel, it's 4 kilobytes. Although you can imagine different machines might have different page sizes. It's not that important, right? So you will also split physical memory starting from address 0 into equal chunks as well, right? And you say, okay, and the hardware will implement some mechanism, which is called page tables, right? And I explain how they work in a second, which will essentially be somehow translating the addresses. So essentially, if this is the virtual address, right? And you say, look, I have my virtual address in this EAX register. I'm trying to access memory and read something into the EBX register, right? I can't really access immediately this address here, right? Because that's not what we want. So you will take this address, the value of EAX register, as an input to the page table. And the page table will produce the corresponding physical address, right? And then the hardware will specifically access this physical address, and the value which is stored here will be loaded in the EBX register, right? And intuitively, it makes complete sense. Like, why not? So you say, look, this mechanism, again, we don't know yet how it works, but it essentially maps every page in the virtual address space of a process into physical page of the machine, right? And since we started splicing this memory starting from address 0, all the pages are starting at 496 byte boundary. So this is 496, and this is 496 multiplied by 2, and this one will be, of course, 496 multiplied by 3, right? And so you say, look, instead of like using the full address, we'll be just using page number. So this is a page number 0, this is a page number 1, this is a page number 2. No, literally, this is page number 0, this is page number 1, this is page number 2, if you're counting from the beginning, right? And this one is page number 3, right? So this number is called a physical page number, and this number is called a virtual page number, right? And so when we take the address, we'll take some part of this address, right? And we say, look, this represents virtual page number, and the rest of the address represents an offset within a page, right? Because page contains some number of bytes. And no matter where it is in physical memory, within the page is like a tiny segment. It's small, it's 496 bytes, right? And within this segment, we can address any byte, right? And to represent 4096 bytes, we need 12 bits, right? So essentially, if total bits is 32, then 20 bits represent the physical and virtual page numbers, and those bits we will be translating. So essentially, the page table will take a virtual page number as an input and will produce a physical page number as an output, right? Is that clear? Right. And so the page tables, what we want to do is, because since we want to achieve this complete control, we want to map any virtual page anywhere in physical memory, right? So this is physical memory. So like translation should be flexible. So hold on, I wanted to explain one thing. So each process will have its own page table, right? So this is a green page table for a green process. For this yellow process, it will have a operating system will configure a separate page table for the yellow process, right? But for each process, like each process will have address 0, this page will be translated somewhere, right? And we want a full freedom for this translation. We want these pages to be anywhere in physical memory, right? So if I ask you a question, how can we build this translation mechanism? This tiny cloud which I was drawing, what kind of a data structure CPU has to implement to make sure that we have this full flexibility of translation? So Surya suggests hash map. That's not a bad idea. Hash maps is one possible way, right? So let's do the simplest one. So maybe linear probing, right? So for example, you say you hash a virtual key, you land somewhere on a hash table, you compare it, like whether it contains this specific virtual, you use virtual address as a key, right? So you compare it if it has this virtual address as a key. If comparison matches, you say, look, yeah, I will keep here physical address and my troubles are over. If not, I will, for example, again, simplest hash table, I will implement a linear probing algorithm. So linear probing means I will go to the next key here, we'll try to comparison against, we'll go to the next, and like depending on the quality of the hash function, but for those small numbers, even the simplest hash functions, like the simplest literally, you don't really need to do anything, like any permutation will do, they will have about the same quality. It works. However, it's a little bit involved because you don't have a predicted time, right? Because you say, look, first of all, some pages will be translated immediately. Since you land on a hash table, you have a hit. Some will require a walk. And also this linear probing works well. I would say it doesn't really work above 87%, 75% full. Then the walks, like, reprobes take so much time that it just like, it will horrify anyone and will kill any performance, right? So this array will have to be rather large, right? And so this is not how it's done. But any other ideas besides the hash map? No. And another intuitive idea is an array, right? So hash map is a glorified array, right? So kind of. And we can say array will work like this. So we will take virtual address as an index, specifically virtual page number as an index. And inside this entry, we will keep physical page number, right? And that's it. Like, it's much easier than the hash table, right? Agree with me? No need to do reprobing. Hash tables are good for specific workloads when keys can repeat, right? So here keys don't repeat. So each virtual page number is unique, right? So arrays would have like a slightly more deterministic behavior. What do you think is a disadvantage of using an array? Memory footprint. Yeah, exactly. So who can tell me what will be the size of this array? Anyone can come up with a number without looking into my lectures? Okay, let me help you here. So 2 kilobyte, you're shy. Let me show you. Okay, so array would be great. So virtual to physical translation array, right? So as I was saying, 20 bits here will be will represent the virtual page number. We'll use it as an index in this specific example in a decimal form. It's 1040, right? And here inside the array, we'll put a physical page number. So essentially, this translates to page number 12, and this is how we want to access. So specifically, we're trying to access this virtual address, but really we go and the hardware uses this array and goes to the page 12, physical page 12, where it uses those bits to offset within a page, right? So I think it means 16. So it will read byte number 16 from that page, right? And for example, you say, look, the operating system can put this array somewhere in physical memory over here, right? And might have a specific register, which is on Intel, it's called CR3 or control register 3, which will keep the physical page number of the page which contains this array, if it fits in a page, or maybe it will take multiple pages, right? As I was saying, I'm asking how big is the array, and you didn't answer yet, right? So, and that's essentially this is essentially the problem. Look at this equation. Let me just switch here. Let me go back just a sec. It will be easier to explain here. How many entries we need in this array? To answer this question, you say, look, I need to translate any of the virtual page numbers which the program might want to use, right? Because if your array is smaller and the program tries to access something over here, array is not even present, right? So the hardware doesn't even know what to do, right? So maybe it can generate exception right away, but ideally we'll say, okay, let's cover all the addresses, right? Even if though maybe maybe the program uses only like a small fraction of those addresses, right? And majority of this address space is empty. So maybe this is a shared library. This is maybe the kernel sits here somewhere, and these are the code plus data sections, and maybe plus stack of the program, right? And the rest of the address space is kind of sparse, right? So how many virtual page numbers do we have to translate, right? The entire address space is 4 gigabytes, right? So it's 2 to the power 32, right? And you say, okay, hold on, I'm dividing this by 4 kilobytes because each page is 4 kilobytes, right? If you do the division, you will get 1 million entries, right? Or exact number is 1048575, right? If you do the division in proper power of 2, right? At this point, you say, so you say, okay, my array needs to have roughly 1 million entries, right? Okay, how large is each entry? Since we say, look, roughly speaking, it's 4 bytes. Really, to represent the physical page number, we will also need only 20 bits. So you can argue that 20 bits is sufficient. But in practice, you also need some kind of bits for flags, right? And you say, look, if here I will put an entry in the array, 20 bits, like here, if this is the virtual address, so this is an offset, obviously, right? So this bits will be 20 bits for physical page number and 12 bits for flags, right? Which means that the whole entry is 4 bytes. So now if you multiply 1 million by 4 bytes, you will get the size of this array, which is 4 megabytes. It's a large array, right? Especially back in the days when, my first machine, which I got as a child, had only 16 megabytes. I think 8 or 16, I think 8 megabytes of DRAM, right? It was Pentium 1, so which was like a huge, super duper machine back then. So with this approach, I would be able to run 1 or maybe 1.5 process on my system, right? So today, of course, it's a less of a concern because now we have gigabytes of DRAM, right? And servers maybe even terabytes. but back then it was a problem, right? So the question is like, how can we solve this problem? So can we change this array somehow to make sure that we can represent this translation somehow more efficiently? And the key insight here is to observe that majority of this address space is not used, right? So only it used sporadically. So something in the beginning, something in the middle, and something at the end, right? And you say, look, I really don't need the entire array. I only need fractions of this array to represent the translation. So do you see a data structure which can represent this this case where the address space really contains a bunch of holes? Linked list. That's not bad. So linked list is coming pretty close. What's wrong with linked list? So who can tell me? Linear traversal, right? Exactly. So, you know, linked list is ON lookup time, which is not ideal, right? Ideally, would like to have something like constant time. Sparse array. So what is a sparse array? So maybe we mean the same data structure, but I just don't know the name for sparse array. A sparse array is kind of like a linked list. But in any case, you're getting there. So you want somehow represent this sparsity, right? So let me explain how it can be done, right? So this is the calculation for computing the size, but we already covered it, so there is no real reason. And here I was suggesting yet another possibility of having an array with size, kind of saying that if you grow your address space from the beginning, you only keep the size, and then, you know, if you dynamically extend it, you can extend the array. It doesn't really work that well because you need like to have continuous physical pages here, and also maybe you really like allocated at some point, you allocated like a whole like 500,000 pages just for some spike workload, and then you deallocated most of it, and again you have those holes which are empty, but your size is still like needs to cover one like all the entire 2 gigabytes of your address space, because half a million of pages is 2 gigabytes roughly, because 1 million is 4 gigabytes, right? So continuous array with pointer at the end to the next one. So it's more or less like a linked list, right? So Yukon says multi-level page table, and this is where I'm getting. So you're right. So what I'm saying is that let's represent this sparsity as an array of arrays, right? Roughly speaking, I'm saying, how about we will have a first level of array, right? So one array, and this array will have essentially pointers. Hold on, let me just draw it slightly differently. So this first level will potentially have pointers to the second level, and each second level can cover a chunk, continuous chunk of an address space, right? But if you don't need the next chunk of the address space, this next pointer is null. So you don't really allocate this second level of translation, right? And if you need to represent this chunk somewhere in the middle of this array, you will again allocate yet another level, and this level will keep translations which cover this chunk. And maybe at the very end, you will have again allocated a chunk, and this chunk will essentially describe translation for this region, right? In this example, your translation data structure, you will need to have a root always, right? And you will have like second level. So this is like, you can say this is level 1, and maybe this level 2. And on this second level, you only allocate nodes as needed. So if you need pages in this region, you allocate a node. If you don't need a page, you say, well, this is null, so I don't need anything, right? This way, your translation data structure can be reasonably small. So imagine your root is, for example, 4 kilobytes, fits in one page, and each level is also 4 kilobytes, right? Then in this specific example, the whole size of this translation unit will be 4 kilobytes by multiplied by 4, right? Or 16 kilobytes, which is just nice. Okay, we just said, okay, like instead of 4 megabytes, we now require only only 16 kilobytes. Of course, there is no magic. If you will be using the entire address space and you really need all the pages here, then you will have to allocate all nodes for the second level, and then the size will be even slightly larger than this 4 megabytes. But the idea is to leverage this sparsity, saying that the address space of the process is most likely sparse, and it's true in practice for most programs, right? And that's why you don't really need to allocate the second level of this array, right? It's a B tree, you're absolutely right. So let me just now explain in details how this data structure is organized. I just wanted to make sure that we understand the motivation. So motivation is to represent this sparsity, right? So I don't even really want to take questions right now because I didn't really explain it that well. So let me explain it a little bit more rigorously, right? So again, just another drawing for this table of array of arrays, which contains, it's a table of regions. And if the region is present, it's green here, we will have a pointer, right, to the bit of memory which contains the translations, which will point us to different physical pages, right, in physical memory. And again, if this is present, then there will be a pointer. But if it's not present, there is nothing, null, right? So this memory, which represents this region, doesn't need a second level. Again, not yet exactly clear how it works, right? But essentially you say, look, I will organize it like that. So my root will be a page, one page, 4 kilobyte. It will contain 1024 entries, right? Because if I divide 4 kilobytes or 496 by 1024, I will get exactly that each entry is 4 bytes. That's what we wanted, right? Because we said, okay, 12 bits for physical page number and not 20 bits for physical page number and 12 bits for the flags, right? Okay, and inside this first level of this first page, and this page will be somewhere in memory. So operating system, we can say, look, operating system will again use this control CR3 register to point to the page. So in this case, it's in the physical page number 2, right? This first level of translation is living there. So, and it has 1024 entries, right? And then for each entry, it might either have a null pointer, like nothing, or it might have a physical page number of the page which contains the next level of translation. So in this example, it's page number 8. And so this page number 8 essentially contains, again, some fraction of this translation array, right? And this translation array will again have 1024 entries of 4 bytes each, right? Because a page is 4096 bytes, right? And again, you might have some nulls, some sparse elements here, which don't point anywhere. But for entries which you want to translate, you again will contain physical page number here, which is, in this example, it's page number 9. And in this example, it's page number F, right? So physical page number F will contain this level 2 array, right? So you got the point. This is level 1, this is level 2, and level 2. And again, as I was previously shown, that this is a 4 kilobyte thing, and you have 4 of those, right? So the total, right now, the total size of the page table is only 16 kilobytes. Again, I didn't yet explain how the translation works, but at least we kind of understand how it gets represented in memory. So let me stop here for a second, because at this point, I think you can ask questions. All good? Okay, let's take a look at how translation might work. Imagine we want to translate, again, in this example, I'm sorry, I'm using this AT&T assembly here, which says that in Intel, it says I'm moving something from the EBX register, from memory pointed by the EBX register into the EAX register, right? And EAX right now contains 0, EBX contains this decimal value, which if we write it in binary form, will have the following format, right? I will answer the question in a second. Okay, the hardware itself, right, needs to keep track of 1 million entries, right? So because each process has address space which starts at 0 and goes to the to the power 32 minus 1, which is 4 gigabytes, right? So if you cut this address space into 4 kilobyte chunks, you will end up with 1 million possible virtual page numbers, right? Right? So how many bits do you need to represent a page number? I already said it's 20, right? So those 20 bits will be representing the virtual page number, right? So this is the virtual page number. And we have to translate it into physical page number, right? Because this part, those 12 bits, are just represent offset within a page, right? Okay. So in this example, the page number, which is encoded here, is page number 5123, right? Or in binary, this is exactly this number, right? So 11, bunch of zeros, 101 here, right? 101 here. And again, bunch of zeros, right? So it's the same page. So this is the page which we're translating in this specific example. Okay, so the hardware itself will have the CR3 register. And as remember, CR3, I'm saying it's initialized with 0. So this answers your question. It can be any page number. The operating system sets it. So operating system says, okay, look, I will load this register with the value of the physical page, with the page number of a physical page, which contains the root of the page table, right? And in this example, I chose 0. Maybe it's a little bit confusing. I should have chosen 1, right? So this is where this page table directly sits, right? As I was saying, it has 1024 entries. And now pay attention. This is how the translation works. Someone says it's a radix tree. Yeah, it's a radix tree. It's not a bit tree, it's a radix tree. Look, we take this highest 10 bits of the address. So we split those 20 bits, which represent the virtual page number, we split in 2 parts, 10 bits and 10 bits. And those 10 bits we use as an index into this page table, into this array. Essentially, right now, the entry is, what is this number, 101? Who can tell me quickly? 7? 5. I'm done, yeah, 5. So this is entry number 5, which we have to choose here, right? In the first level of a page table, because this number, binary 101, is equals to 5, right? Okay, we chose entry 5. And what's inside this entry? Inside this entry will be a physical page number of the next level of the page table. So specifically, let's imagine we have 7 here, which means that in this page, physical page number 7, there's the next level which corresponds to this specific translation, right? So it's a page table level 2. Again, the same 1024 entries. Now we say we'll take the next 10 bits of the address, so those 10 bits, and use them as an index. So 11 is 3, right? So we'll choose entry number 3, right? And this entry number 3 will be containing the physical page number. Essentially, the physical page number is 12 in this example. And this is where exactly this data, which corresponds to this page, which we're translating, is sitting, right? At this point, so essentially, we went through two levels, right? Level 1, and then we chose level 2, right? There are multiple level 2s, right? Because this might point somewhere, this might point somewhere. Maybe the rest of them are nulls, for example. Maybe we're translating only some fractions of this address space, right? But what happens is that now we have to find an offset within a page, and this is a byte number 1, right? Because it's binary 1, so it's byte number 1, right? So within this page, we'll pick specifically byte number 1, which contains 55. So essentially, if we're reading just one byte value, then this 55 will be loaded in the EAX register, right? Okay, now let me stop here. So is it clear? So this is how the translation works. So I will be asking a lot of questions about it. So you have to understand how it works. So think about it. And if something is not clear, even the slightest thing, I will explain again. Are level 2 tables continuous in memory? No, because this can be 7, this one can be 120, 1025. And you will go over here to this page 1025 in physical memory. And this is where this level, second level, L2 for the address, which lands you not on 5. If this changes to 110, it lands you on 6. And then your second level will be in a physical page 1025. Right? And this is configured by the operating system. When operating system creates a process, it reasons about which physical pages are still free. And it says, okay, I will allocate as I will be creating the page table, and you will see this, how it will work when we will be creating the first process, and then we'll be going through the exec system call, or maybe even slightly in the opposite direction, first exec and then the first process. The operating system will say, okay, which physical page is free? If the allocator says it's page number 13, it will put page number 13 here. Which one is next? It's page number 7. Which one is next? Page number 1025. And that's why you can completely end up with some random pages in the second levels, because there will be an allocator which will be keeping track of available physical memory, and you will be just filling in those entries to set up the page table for this process, right? Anything else? So specifically the root of the page table, we can change this from 0 to 1, then the root will be sitting here, right? You can even do tricks like, I mean, I don't want to confuse you, but let me just quickly erase or link on this slide. But this 7 can, technically speaking, look back to this 0. You have to be careful. The hardware will blindly follow, because the hardware doesn't really care. And if you can create a correct page table in such a manner that this will mean something, it will represent something meaningful, and it's actually possible, then go for it. So there is no restriction. This 7 can be changed to 0, right? And you can loop back if you want. Our level, no, any other questions at this point? All good? Everyone's clear? Okay, excellent. I will be asking questions about page tables. Okay, so this is the final bits of those slides. Okay, just again, recap for the translation. We have linear address, which is the result of the segmentation, right? How we translate. The hardware picks up 32, the physical address, which is 32 bits of the page table directory. So this level, something what I was called level 1 is called on Intel page table directory, right? So then it takes highest 10 bits of the address, uses them. So this is like 10 here, it means 10. It uses them as an index into this page table directory, right? It picks up the entry, and it's a page directory entry. PS is set to 0. I'm not sure what it means. Let's skip it for now. Here it reads only 20, right? Only 20 bits. Why 20? Did we get it already? Because the physical page number of this page table array, right? Since everything is aligned at 4096 byte boundary, right? You only need 20 bits to represent the address, right? Why is that? Because the lowest 12 bits are always zeros anyway, so there is no reason to keep those zeros around. And instead of like keeping those 12 zeros around, right, you can use some space for flags. So there will be flags here, right? So, and this is a specific format here, right? So this is the address of the next level. So the highest 20 bits, right? And the rest are the flag, right? So I explain it one more time in those slides. So pages are 4 kilobyte each. We need 1 million, right? So that's why you took this 20, and I will come back to those flags in a second. You took this 20, so this is a physical page number on the second L, like level 2, right? Again, you take 10 bits of address, those 10, you use them as an index into this page table. So, okay, just again, if all of these are zeros, if all of these are zeros, right, it will land you on entry number 0. If all of these are binary ones, right, it will land you on the last entry, which is 1023, right? This is clear. This is how it works, right? And again, here we, in a very similar manner, read only 20 bits of physical page number of the actual physical page, which contains the data, right? So we use the offset of those 12 bits here to encode any of the 4096 bytes on this page, starting from byte number 0, 1, 2, and up to 4095, right? And again, let me get back to flags. So what are those flags here, right? I guess I didn't have a good slice on flag. I used to have, maybe deleted accidentally. Let me go back. So those flags will encode things like this bit number 0 is whether the entry is present or no. So if this is not set, if this is 0, it means like it's null, it's not pointing anywhere. This entry is invalid, right? Then you can say, is this page readable or writable? So this is the read-write bit. Is this page user accessible or only super user? Remember, we know that the segments encode the code privilege level, and specific operations and specifically translation will only go through if for the user pages if this user bit is set to 1. So this is how you can isolate kernel from the user. So the kernel can be mapped as well, but this bit will not be set. This will be 0. And this way, if the user which runs at privilege level 3 will try to access an address which goes through this translation, the hardware will stop it and cause an exception, right? And you can actually do a tiny exercise on QEMU later on when you learn how to boot into the machine. You can actually, or even like you can boot into x86 if you want. I mean, I don't know if you can right now, but you can run this experiment and catch and figure out which exception are you catching actually, right? So there are some other flags, right? Whether the page was accessed, whether the page was accessed, it allows you to operating system to track pages which were accessed by the program, right? So it's used by, for example, if you're trying to implement an algorithm which decides which pages of the program choose for swapping out, you say, look, I know that those pages, you keep tracking which pages are accessed frequently, you can contain some metadata, and then you say, look, by the way, those pages which are not accessed frequently, I will take them out and put them to disk, right? There are some other bits like this one is dirty, meaning that there was a write in this page, and it's useful for process migration. For example, when you migrate processes from one machine in a data center, or like maybe you're migrating not the processes but virtual machine, so right over the networks, essentially you're moving the entire VM from one node in the network into another. You first will copy, like you let this machine run because you don't want to introduce interruption, right? So you copy all the pages over, will create an identical virtual machine, right, in memory by copying just all the pages like in memory. But while you were copying, of course, some pages of this VM got dirtied, right? Because there were writes into those pages, right? And you say, okay, look, I will do another iteration of this look, and I will copy again those dirty pages over, right? And while copying again, maybe even more pages get dirtied, but the set of these dirty pages will be gradually decreasing, right? And at some point you reach a point saying, okay, maybe some small number of pages is dirty. I will pause this VM, will copy the pages over, and essentially we'll never run this VM again, but we'll run this copy, right? So because at this point you say, I will resume on another physical host, and I will, if your network is smart enough, all the next incoming packets will be routed to this VM, right? So this is why you might use this dirty bit, right? So this iterative kind of migration protocol, right? It's quite common in data centers today, because that's how you implement, like this elasticity and kind of saying, okay, like this machine got overloaded, so let's move VMs around. They need a little bit more CPU, or this machine has to be taken down for maintenance, stuff like that, right? Okay, good. And of course, yeah, the offset. So we got this. Okay, what are the benefits of page tables, right? What did we really achieve with them, right? Because we said we started with the segmentation. Segmentation was working quite okay, but there were some flaws, and we discussed them today early on, right, in the lecture. So what we achieved is that the page tables represent sparse address spaces more efficiently, right, compared to arrays. So here I'm comparing with arrays, not with segments. So compared to arrays, instead of like keeping the entire 4 megabytes of translation, because you have to always translate any of those possible entries, you say, look, I have this tree. My first level is always there, but entries, and it's a radix tree of a radix of 1024, right? If you want to like know the exact definition. And some leaves are present. So, you know, as if I use this part of the address space, I will add this leaf. If I use this part of the address space, I will add this leaf and then this leaf potentially, right? And so this data structure allows you to represent a sparse address space, right? Again, I can ask you a question. What happens if you're using the entire address space and you need all of those leaves? What will be the size of this data structure? Can someone quickly tell me? Anyone? No, like it's an easy mathematics, right? The first level contains 1024 entries, right? Which means that if you're using the entire address space, you will need to allocate 1024 pages, which are 4 kilobytes each, right? So it means that it's, again, we're back to the same 4 megabytes, but there is plus additional page, which is plus 4 kilobytes, right? So which is slightly larger than the array, which is only 4 megabytes, right? Exactly, Yuan. Yeah, you're right. Okay, but you got the point. But the point is that most likely it will get sparse. And even if it gets full, you only larger by 4 kilobytes, right? And you can dynamically allocate and deallocate level 2 nodes, right? So you can, as long as you, if you spiked, used all the memory, deallocated them again, you just deallocate the second level nodes, and you again like back to some small number. What about isolation, right? So with segments, we understood how isolation is achieved, right? The segments essentially, remember, this will have a base, will point somewhere in physical memory, right? And this will have a base and will also point somewhere in physical memory, right? And those guys will not overlap. So this one, physical memory of process P1 and physical memory of process P2 will not overlap, right? Because we will choose, operating system will choose and configure different bases, right? How do you think it's achieved with page tables? Anyone? No conflicting page tables between processes. Exactly. So here I have an example, again, of a green process P1 and a pink process P2. Each process will have its own page table. The green will have its own and the pink will have its own. They will be somewhere in physical memory, right? And separate, like, of course, like collection of pages. You know, we know now that it's not a single page, right? And as I said, like each process will have kernel mapped in their address space, right? So there will be a yellow part, and the yellow part will be mapping the same yellow pages, right? But the point is that the mappings for those pink pages and the mappings for the green pages will never overlap, right? And so no matter which address the pink process issues, it will always land on only on pink page, right? This is how isolation is achieved. If operating system is careful enough not to make sure that they don't map the same physical page, they cannot really overlap, right? This is isolation. Agree with that? So this is great. So, and compared to segments, right? Like we have much more flexibility, right? So in our example, we only had 12 physical pages, right? But as someone mentioned before, we can emulate a much larger virtual address space on a smaller physical memory. The idea here is that your address space can be large, and you say, look, you can say, the moment you access this page, if it's not present, if it's not mapped in any of those 12 physical pages, right? It's not in a page table. So this, remember, bit 0, which is a bit present, is equals to 0, right? Then, okay, translation causes a page fault. Page fault goes to the operating system. Operating system says, okay, look, I know that the program tries to access this page. I will go to disk. I will allocate one physical page, move the data from disk, right, into this page, and I will fix the translation. to make sure that, now this present bit is not 0, but 1. And this, you execute this move instruction again, resuming from exception, and everything is like transparent to the program, right? So this is nice. You say, look, I can take away memory page by page. You could have done it with segments, but with segments, it's a little bit much harder. So you have to like compile your code in such a way that it uses different segments. And this is how it was done in the past. But thanks God, we don't have to do it anymore today, right? So this is great. And also paging becomes much faster. So all these fragmentation issues disappear because the granularity is a page. And you say, look, I take it out, I put it back in, right? Okay, so pages also allow us to selectively share memory. So in this example, you say, look, I want these two processes to share memory. Maybe this is a shared library like lib.so, which we were discussing in linking and loading. So you allocated once in the physical memory and then map twice or more than once in different processes, right? And because of we know how position independent code works, right? So those can be mapped at different addresses. This is address A and this is address B, but because of position independent code, it still works, right? Okay, cool. So, or you can use those pages for shared memory and communicate between processes. So maybe this process is a compositor. So for example, you use this one as a frame buffer where essentially the GUI libraries which run inside this program put like the view, like the window of like whatever, the buttons, some kind of picture here, right? In this frame buffer, and this compositor essentially has shared frame buffers with all processes, with all graphical processes in the system. So it copies them over here, or even like it doesn't even have to copy, it just looks at them and composes like a single view in which this figure might be under some other application, because you just put one on top of another, right? So this is how it's typically implemented, right? Because pipes are good, but pipes are reasonably slow. But when you share memory directly, whatever you write here immediately appears here, right? Because it's the same physical memory. So really write goes here. So the moment this process has a chance to run, it will immediately read the same memory, right? Okay, so this is nice. Let me just go one more time over the entire translation process, right? Remember, CPU starts with this logical address, which will contain two parts. It will have a selector part, which will be in one of those segment registers, CS or DS, right? So on Intel, it's impossible to enable paging without enabling segmentation. So you start in physical mode, but then you enable segmentation, right? And then you enable paging, right? Then offset is inside the register, and these two guys are together called logical address, right? These two guys go as input into the segmentation, right? Remember, we choose an entry, selector chooses an entry in the global descriptor table, offset is added to the base, which is read from the global descriptor table, right? And it produces a linear address. And this linear address is also known as virtual, right? So typically people say virtual here, right? But Intel has a specific name, linear, right? And this linear address goes as an entry to the page table translation unit, which produces a physical address, right? And this physical address goes to DRAM, right? Okay, let's go again one more time through like individual parts of this translation on the Intel diagram. So segment selector and offset. Offset is in register, for example. Segment selector grabs something from the global descriptor table. Remember, there is a special register, GDT register, which holds the base of this table. We get the linear address by adding the base, should be plus here. It's actually a diagram from Intel, they can do it a little bit better, right? And at this point, segmentation is over. So you're done with the segmentation part. Now this linear address goes as an input into the paging unit, right? And again, remember the split, we take 10 bits of highest 10 bits of address, use them as an index, read an entry from here, figure out this page table, next level, physical address of this page table, take these 10 bits as an index, again, figure out this entry, this produces a physical address, and then the offset essentially chooses this specific physical address within this physical page, right? The reason I'm going over it again, if you start reading Intel manual, this is how the diagrams look. The might scare you a little bit at the beginning, but really it's exactly what I just explained. So they just explained the same, right? So you're ready to read the Intel manual now, which is a great thing. A couple of details which are important again for this graduate level class. So 32-bit architecture supports 2 page sizes, 4 kilobytes and 4 megabytes. Who can tell me why do you think it's done? What's the importance of this? Why do you need suddenly larger pages? Prevent thrashing, decrease thrashing. What decrease? So remember, we were fighting with segments. Segments were large and bulky, and pages are smaller. But suddenly we're back to pages which are 4 megabytes, so larger pages. Why do you think this is done? Decrease page table lookups. Exactly. So it's to decrease the cost of page table lookups, because each page table lookup has to read this entry from memory, right? Like this is a page table directory. In order to do the translation, this is in memory, right? So you have to go to memory. And remember, a trip to memory is 200 cycles in the best case. Of course, CPUs are clever. They have a special cache on board, which is called translation look-aside buffer, or TLB. It will cache frequently result of frequent translations. And also there will be, this results will be also cached in like I think L1 cache as well, right? Like everything will be cached, right? TLB caches directly the result of the translation. It can be produced under 1 cycle. And then the whole entry can be cached in L1 or can be cached in L2, for example, right? Or even in L3. So it's not always 200 cycles, right? But if you truly accessing random memory in a random manner, like imagine your hash table takes the entire 4 gigabytes, right? So it's just one giant hash table, and you're running Facebook, like you don't run any other applications. You say, look, I will be running just the hash table, and I will be like, the whole data center will be running just the hash table, like what is it called, memcached, right? And I will be looking up parts of my whatever Facebook pages and those hash tables. And you say, look, but it's truly random. And the TLB, you know, the hit in the TLB is unlikely. The hit in the L1 for this page table directory is likely, or in L2, but maybe even the hit in L3 for the next level of translation is less likely, because even, remember, the entire page table hierarchy takes 4 megabytes, right? And depending on the size of your L3, and today they range from like from 2 megabytes to roughly even like 32 megabytes, right? This can fit on a beefy server machine, but on a tiny laptop machine, it will not even fit. The entire second level will not even fit in a last level cache, right? So you will at least pay 200 cycles here. And that's why they said, okay, look, forget about it. For those workloads for which we don't need like fine granularity of memory management, because it's just one giant page table, it will always be using the entire address space. Instead of 2 levels of translation, we will be using just 1 level. And this 1 level will have 1,024 entries like before, but it will be immediately directly pointing to the physical page numbers of pages, right? But since the entire address space is 4 gigabytes and you have only 1,024 entries, you have to divide. And the size of each entry is what? Is 4 megabytes, right? That's exactly as you're saying, look, my pages will be 4 megabyte pages. There will be 4 megabyte page number 0, 4 megabyte page number 1, 4 megabyte page number 2, stuff like that, right? So that's a trade-off, but you don't have to go to the second level and translate yet another page. So you will save potentially 200 cycles here. So the equation gets a little bit more complex, but essentially your goal is to understand this insight, that the idea of those super pages or huge table pages is to essentially reduce the cost of lookups in a page table, because if you're running a truly random memory access workload, then you might start experiencing, like, instead of like actually reading the data, which will cost you like 200 cycles, now you will have to read a second level page table entry, which will cost you 200 cycles, and then the data. So essentially your data access, like the cost of data access doubles, right? So that's why the hardware architects came up with this with this idea, right, of saying, like, we're not going to do this. We will introduce this idea of super pages or 4 megabyte pages. Can two segments share a page table directly, even if they don't share a page? Can two segment? I should admit I don't really understand your question. So maybe let's take it offline because I am not exactly sure what you're asking. Okay, the page table translation for these 4 megabyte pages, exactly as I said, but a little bit tricky, right? So hold on, let me go back here for a sec. Back. So now, since the page is 4 megabytes, to index any of the bits, you need to know, like, how many bits for the offset? 22 bits. So bits from 0 to 21 are now the offset, and bits from 22 to 31, it's again the same 10 bits here, and this is the same 22 bits, right? It just, we split them differently, kind of cute how it works, right? So those 10s choose an index from the page directory. The CR3 still points to the page table directory here, right? But each of these entries, since now you only need 18 bits to represent the physical page number of a 4 megabyte page, so you read only 18 bits and get the physical page number of this page. I also wanted, since we have still have four minutes here, I wanted to make sure that you understand how page tables work on 64-bit machines. So this is one difference, and I want you to know how it works, because normally 32-bit mode and 64-bit mode is very, very similar. Remember, I forgot if it was there in this lecture about position independent code, but essentially, when Intel moved from 32-bit machines to 64-bit machines, they introduced a special addressing mode, a new addressing mode, which is relative to instruction pointer, which would allow you to, instead of doing this thunk trick with learning, which is where's my IP current instruction pointer on 32-bit machine, and then adding it to figure out, and then adding an offset to figure out the address of the global, what is it, global offset table, right? You can just say, okay, use IP and say plus offset and just directly go into global offset table. So that, because position independent code was gaining popularity, and Intel just did a fix to make sure that the code runs a little bit faster. It was natural. So that's one difference. And this is the second difference, which is kind of like significant, right? So in order to encode, there is a tiny wrinkle. We say 64-bit mode, but Intel, up until recent years, allowed only 48 bits of virtual addresses. They said, okay, that's just enough. You don't really, like, physical memory is still, like, you don't really need larger address spaces. Now they bumped it up, right? So now there will be 5 levels of those page tables, but here it's 4. So essentially the same idea. So you take 9 bits here, 9 bits here, 9 bits here, 9 bits here, and 12 bits here. And it adds to 48 bits, right? So again, why is it 9 suddenly? So you used to have 1024 entries, right? And everything was fine. The wrinkle here that these entries were 4 bytes, but to represent a physical page frame number of a giant physical memory, which can have up to 55 bits of addresses, it's not enough to have 20 bits. You need 40. So, and 40 doesn't fit the plus flags. It doesn't fit in 4 bytes, right? So that's why the entry, each entry is now 8 bytes, right? And since it's 8 bytes, instead of like 1024 entries in a page, you will have half of them. So it will be 512, right? And to index, to index into one of the 512 entries, you don't need 10 bits. You only need 9 bits, right? So the same idea though. So first 9 bits of the highest 9 bits of this 48-bit address. The CR3 has a pointer to it's called now PML L4, essentially level 4, and other levels will have addresses, will have special names. So this is L4, this is L3, this is L2, and this is L1. So essentially, like they name them in a reverse order, right? So this is still called a page table directory. This is called a page table, page directory pointer table. Of course, how else? What else could it be, right? Page table directory pointer table. This is funny, right? So just call them L4, L3, and L2, and L5. And now Intel added one more, which will be L5, which is like will be in front of it, right? But you got the point. So like first nine bits, index get an entry, it produces a 40 bits of physical page number for the next level. Then you use the next 9 bits here, index into this one. This again produces the 40 bits of the page table directory. It's a physical frame number which contains this page table directory. Again, you take those 9 bits, use them as an index. So it's a radix tree, but now it just has more levels. So 1 level, now we used to have only 2. Now we will have 4 levels, right? So up to 4 levels, right? So, and of course, at this point, these tricks with super pages become even more important because you say, look, even those guys did not fit in like in the last level cache, which was L3, right? Which is up to 32 megabytes. But imagine like your address space actually uses all these entries and the translation like goes through, right? So that like even more cache misses. So that's why on 64-bit mode, we even have, we will have corresponding sizes for each of those levels. So essentially there will be a mode in which, oh, hold on. Oh yeah, it still works. Let me just a sec. A mode in which only one root will be present and it will be indexing into 1 gigabyte pages, right? Again, 512 multiplied by 1 gigabyte, the entire address space will be 512 gigabytes, right? So that's what Intel was allowing you to address with 48 bits. Or you can have a size in which you'll have 2 levels and each of those guys, and at this point, it's hard for me to do the math. I can do it backwards. If you have 3 levels, and if you have 4 levels, right? If you have all 4 levels, then your page is still 4 kilobyte, right? If you have 1,000 of this one, oh, it's not 1,000, it's 512. So this will be a page of a size 512 multiplied by 4 kilobytes, which is 2 megabytes, right? And again, 512 of 2 megabytes. Am I right? Yeah, will be what? Who can tell me? I wanted to say, no, yeah, there should be a page of this size. Okay, I cannot compute it. What is that? I somehow come up with 1 megabyte to one gigabyte. So maybe I missed something here, but along those lines. So those will be all possible page table sizes, right? So essentially 1 gigabyte, right? So I was coming up to 1 gigabyte, but then what's this intermediate size? That's what I cannot figure out. So 1 megabyte. Something is missing in my logic. But anyway, so you got the point. So this is how it works, and I can come up with exact sizes next time. So this is it for the paging, right? So I hope you understood how it works. So next week, we're going to spend on midterm recap and the midterm itself. And then the week after that, we will start booting in main, right? So essentially, I will explain how boot works, and your homework assignment then will be to essentially just write a piece of code, which essentially you can plug it into the machine. We'll be using a QM simulator, which essentially can boot on your hardware, right? And we'll print hello world. So that demo, which I was showing in the beginning of the class, you will actually implement that demo. So okay, thank you for your time today, and I will see you then on next week on Monday. If there are any questions, I can hang out here, but you probably should run to your class.
Yeah, I have a question. Like, can a process have mixed page sizes, as in like?
Right, it can. This is quite amazing. So on each level of this translation, there will be, when you're traversing the entry, there is a flag which says, okay, is the next size present or not? And it can say, look, no, it's not present. And you will like, you can mix those sizes. So you can say it's either go to the next, and then it will be 4 kilobyte page, or translate this one as a one single 1 megabyte page. And we use this in practice because sometimes you say, I would like to split my address space in large chunks, because it saves translation, but maybe you say, look, this one page contains code, data, and stack, and they need to have different flags. So code has to be executable, data has to be writable, right? And then you will split into sub pages, right? This way. Good. Did I answer your question?
Yeah, got it.
Okay. Does it take more time to do translation in 64-bit mode? Yeah, it does. So as you say, you have to traverse through more levels of page table, and despite the fact that CPUs try to aggressively cache translations in the TLB and in various levels of caching hierarchy, still your probability of first missing, TLB is higher, then missing L1 is higher, missing L2 is higher, missing L3 is higher, right? Depends on your workload, but it absolutely takes longer. That's why the rule of thumb is to try to aggregate as many small pages. If you have a continuous address space and you say chunk of address space and say like it's continuous, it can be 1 megabyte, aggregate and introduce 1 megabyte page. And if you have continuous pages of 1 megabyte, and how come I cannot really like do this multiplication? Let me quickly do it. Python 1024 by 1. Oh no, it's 512 by 1 MB, 512 megabytes. No, but it's by 2. Yeah, so 1 gigabyte. Where did I miss the mass? 512 by 4. It's 2 megabytes. And 512 by 512, 1 gigabyte. Yeah, I mean, I don't know, maybe let me look it up in the manual. So I'm confused a little bit, but fine. So, okay, good. Or any other questions? Okay, stop the recording. Thank you, everyone. So see you Monday.